Okay, let's talk about the second way in which small particles, especially molecules, can emit and absorb light. But before we do that, I just want to talk about tuning forks a little bit. Now, I think you've probably all done the experiments where you hit one tuning fork and it starts to vibrate, and because it's vibrating, another tuning fork of the same resonance frequency will also start to vibrate without being hit. And actually, if you had a third tuning fork, the second tuning fork would make the third tuning fork vibrate as well. Now, a similar process happens with molecules, but instead of sound waves, electromagnetic waves instead. So we're going to be looking at the gas molecules and how they emit and absorb energy. So can you remember, if we look at this diagram right at the top of an electromagnetic wave, if we have a changing charge, for example, it's going from positive to negative to positive, we can actually create an electromagnetic wave. So this changing charge, we could actually call it a changing dipole. A dipole is where you get positive and negative, right? But here it's changing, so we'll call it a changing dipole or a dipole moment. Now, another way in which light can be created is if molecules can create a changing dipole or a dipole moment, and this dipole moment creates infrared radiation or infrared light or heat. Now, some molecules in our atmosphere can vibrate, and we're going to be looking at these different vibration modes. So what I've got on this diagram here is a CO2 molecule. Now, what I want you to imagine is that the bonds, or how the atoms of the CO2 molecule are joined together, they're not rigidly fixed. Yes, you can sort of imagine there's a force between the atoms. So the blue atoms here are the oxygen atoms, and the atom in the middle is a carbon atom. And quite a nice way to imagine how they're joined together is just imagine that they're joined together with springs. Well, you can imagine that these springs, if you were to, for example, hit the oxygen molecules with a hammer or something like this, the whole molecule would start to vibrate, and it would start to vibrate at a frequency depending on the natural resonant frequency of the spring and how heavy the molecules are. A little bit like your tuning fork. But as soon as it starts to vibrate, it also starts to release energy as well, and it releases this vibrational energy as infrared radiation or infrared light. Now, carbon dioxide, or the carbon dioxide molecule, they can vibrate in many different ways, and not all the ways of vibration will emit infrared radiation, and we're going to have a look at that. What you need to remember is, if we go back to this diagram, this shows a changing dipole, and the changing dipole is creating an electromagnetic wave. So that's what we're going to be looking at when we're looking at the modes of vibration. Let's look at this mode of vibration here. What's happening is the oxygen molecules are vibrating in and out, and so the molecule is staying symmetric all the time. And because it's staying symmetric all the time, it's not actually changing the electric field. So there's no changing dipole. So that's why I've marked it with a cross, because there's no changing dipole. But if we look at this diagram here, the carbon is shaking from side to side like this. And when it's at one side, it changes the electromagnetic field, and when it moves to the other side, it changes the electric field, and the electric field around the whole molecule changes, and because of that, it actually does release infrared radiation. Let's now have a look at this vibrational mode. So here, the carbon molecule is going up and down and up and down. So here I've shown the carbon molecule as down, and you can see at the top of the molecule it's going to be more negative, and at the bottom of the molecule it's going to be more positive. So here also carbon dioxide can both receive and emit infrared radiation because of the changing dipole. So just to summarize, with carbon dioxide gas in this first diagram here, in this form of vibration, it cannot emit or absorb infrared radiation. In the second example for carbon dioxide, yes, if the carbon molecule is vibrating between the oxygen molecule in a movement like this, then we are going to get a change in the electric field around the atom, and it is going to cause a dipole, which will mean that the molecule can both emit and absorb infrared radiation. And in the final example, yes, there's also a change in the electric field, and this will cause a changing dipole as well, which will allow infrared radiation to be absorbed and emitted from this molecule. When a molecule can absorb or emit infrared radiation, the term we use is it's infrared radiation active. So yes, CO2 is definitely infrared radiation active. Let's have a look at some other molecules in the atmosphere. Now, both oxygen and nitrogen are not infrared active. They do not emit or they do not absorb infrared radiation. And there are two reasons for that. If you look at both molecules, the atoms relative to each other have the same charge, right? Therefore, a dipole cannot be created. Secondly, they're always symmetrical. No matter how they vibrate, they will always be symmetrical. So it's impossible for oxygen and nitrogen, the oxygen and nitrogen in the atmosphere, to be infrared active. So oxygen and nitrogen do not emit and absorb electromagnetic radiation at the infrared frequencies. Okay, let's now have a look at water. If you look at water, the molecules are sort of in this shape, and so it's already got a dipole movement. At the bottom of the molecule it's negative, and the top of the molecule is positive. So no matter how it vibrates or turns or twists, it's going to be creating infrared radiation or absorbing infrared radiation. So yes, water is infrared active. So just to conclude, carbon dioxide is infrared active and can both emit and absorb infrared radiation. Water can both emit and absorb infrared radiation, but nitrogen and oxygen cannot absorb and emit at the infrared radiation frequencies. Finally, I didn't mention it here, but CH4 methane. CH4, because of its molecular structure, is very good at absorbing and emitting infrared radiation. Okay, that's the end of the lesson. See you next lesson. Bye.